Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point and you will not miss a thing. Tonight we are going to talk about Mars, slowly, without hurrying. On a clear night, with no instrument at all, Mars presents itself as a single steady point of light, no broader than any of the stars around it, and for most of the time it is unremarkable enough that a casual glance would pass over it. What separates it, when the sky is dark and the eye has had a quarter of an hour to settle, is its color. It is not red in the way a warning lamp is red, but a soft ochre, a dull orange with something of dried clay in it. And it holds that tint whether the planet sits low in haze or high overhead. The color comes from the surface itself, from fine dust rich in iron oxide that covers most of the planet and reflects sunlight with a reddish cast, so that the tone reaching the eye is, in a real sense, the color of the ground. The unaided eye is not good at judging color in faint light, and the reddish stars of the sky can be mistaken for Mars by anyone who does not know the constellations well. Aldebaran, in the head of Taurus, has a similar warm hue, and Antares, in Scorpius, carries a name that the Greeks understood as a rival to Ares, their name for the planet, which suggests that the resemblance was noticed and remarked upon in antiquity. The difference is that the stars keep their places relative to one another, night after night, generation after generation, while Mars does not. Watched for a week, it holds still enough. Watched for a month, it has clearly shifted against the background, and watched for a year, it has traveled through several constellations, sometimes forward, sometimes back. The forward motion, which is what Mars does for most of the time, carries it eastward through the zodiac at a rate that an attentive observer can follow with a fixed landmark and a little patience. In a single night, the shift is too small to see. Over 10 days it is obvious, perhaps 5 or 6 degrees, which is roughly the width of 3 fingers held at arm's length. The planet completes a circuit of the sky in something close to 1 year and 10 months, and during that circuit it passes near the same bright stars and the same recognizable groupings, which is why the zodiac took the form it did. A band of constellations along which the wandering lights could be filed and labeled. Along with position, brightness changes, and it changes by a great deal more than most people expect from a planet. At its faintest, when Mars lies on the far side of its orbit and is seen close to the direction of the Sun, it is an ordinary point of light of no particular distinction, comparable to a middling star, and easy to lose among the others. At its best, it outshines every star in the sky and rivals Jupiter, hanging in the south at midnight with a color so obvious that people who never look at the sky notice it and ask what it is. The whole swing occurs over a little more than 2 years, so the planet has a slow rhythm of prominence and obscurity that repeats within the span of ordinary memory. The moments of greatest brightness are the oppositions, when Mars stands opposite the Sun, as seen from Earth, rising in the east as the Sun sets in the west and remaining visible all night. These occur at intervals of about 2 years and 7 weeks, or in round numbers, 780 days. And they were among the events that ancient watchers recorded with the most care, because they are unambiguous and because they mark the middle of the period when the planet is easiest to follow. Around each opposition, for a stretch of weeks on either side, Mars does something that the fixed stars never do. It stops, reverses, and travels westward through the constellations before stopping again and resuming its eastward course. The reversal is called retrograde motion, and for Mars it lasts something on the order of 10 weeks, during which the planet retraces perhaps 10 to 20 degrees of sky. Because the planet's path is slightly inclined to the ecliptic, and because the geometry differs from one opposition to the next, the reversal does not usually trace a straight line back and forth, but a shallow loop or a zigzag, its exact shape depending on where the reversal happens to fall. Anyone who plots the planet's position on a star chart every few nights across half a year will draw that loop without intending to, and the drawing is the same one that occupied astronomers for the better part of 2,000 years. The explanation, in the arrangement now accepted, is that the Earth moves faster along a smaller orbit and periodically overtakes Mars on the inside, so that the outer planet appears to slide backwards for a time in the same way that a slower vehicle appears to move backwards when a faster one passes it. None of the early observers had that picture, and it is worth remembering that the loops are not an illusion in the sense of an error. The planet really does appear to move that way, and any account of the heavens had to reproduce the appearance. What differed from one culture and one century to the next was the machinery proposed behind it. There is a further irregularity that the naked eye registers over decades. The orbit of Mars is noticeably out of round, more so than that of Earth, with an eccentricity of roughly 9%, so the distance between the two planets at opposition is not always the same. At the most favorable oppositions, Mars comes within about 56 million kilometers and appears strikingly bright. At the least favorable, it stays beyond 100 million kilometers and, while still conspicuous, is a good deal dimmer. The favorable ones cluster together and recur in a cycle of about 15 to 17 years, which means that a person who watches the sky across a long life will see 2 or 3 of them, and will remember the difference between those years and the ordinary ones. The Babylonians kept the earliest surviving records detailed enough to work with. Their scribes maintained running observational accounts, noting for each planet the dates on which it first appeared before dawn, disappeared into the evening twilight, stopped, reversed, and stood opposite the sun, along with the stars it passed near. From centuries of such notes, they extracted repeating periods and used them to predict what a given year would bring. And for Mars, they found that 47 of its synodic cycles fit neatly into 79 years, which allowed them to forecast the planet's behavior by reaching back to what it had done 79 years earlier. That method required no model of the heavens at all, only long, patient bookkeeping and the confidence that the sky repeats. In Egypt, the reddish planet was associated with Horus in one of his forms, and its name in some texts carries the sense of redness, while temple and tomb ceilings show the wandering lights arranged in registers among the decans and the constellations of the northern sky. Egyptian astronomical practice was tied closely to the calendar and to the timing of ritual, and the surviving material tells us more about how the planets were placed within a cosmological order than about the precise dates of their reversals. Chinese observers gave Mars a name that has been rendered as the fitful glitterer, or the sparkling deluder, a reference both to its changing brightness and to the way it appeared to wander unreliably. Court astronomers were expected to record conjunctions between planets, close approaches to bright stars, occultations by the moon, and unusual configurations, since such events were read for their bearing on the affairs of the state. And these entries were copied into the dynastic histories. The result is a long, dated series of sightings that modern astronomers have been able to check against computed positions, which makes the Chinese records useful both as astronomy and as a means of fixing chronology. Greek astronomy took the same appearances and set itself the problem of accounting for them geometrically, with combinations of uniform circular motions. Eudoxus proposed nested spheres turning on different axes, an arrangement that produced a figure-of-8 motion and so a kind of retrograde loop, though it did not match the observed brightness changes. Later work introduced circles carried upon circles, and Ptolemy in the 2nd century assembled a system in which Mars required not only such a circle but an additional device, an offset center about which the motion was taken to be uniform in order to reproduce the planet's uneven progress. Mars was consistently the most difficult of the wandering lights to fit, and the reason for that difficulty lay in the shape of its orbit, which no one yet suspected was anything other than a circle. For a very long time, the difficulty of Mars was treated as a technical inconvenience rather than a sign that something in the underlying picture was wrong. And the reason is straightforward enough. The accumulated observations were not accurate enough to force the issue. Positions recorded to the nearest fraction of a degree, taken with instruments of modest size, and read by observers working without any means of magnifying what they saw, could be reconciled with circles and more circles if one was patient and willing to adjust the numbers. The tables built on that basis drifted, sometimes by a degree or more, and each generation of astronomers renewed them by tinkering rather than by rebuilding. What was needed before the shape of the orbit could be recovered was a body of measurements several times more precise than anything then available, gathered over enough years to cover many circuits of the planet, and that body of measurements was assembled by one man in the closing decades of the 16th century. Tycho Brahe was born into the Danish nobility in 1546, and by his early 20s he had concluded that the existing planetary tables were unreliable and that the remedy was systematic, repeated observation rather than fresh theorizing. A new star appeared in Cassiopeia in 1572, and his careful demonstration that it showed no measurable shift against the fixed stars, and therefore lay far beyond the moon, established his reputation. 4 years later, the Danish king granted him the island of Hven in the sound between Denmark and Sweden, where he built an establishment called Uraniborg, with workshops, a printing press, a paper mill and quarters for assistants, and later a second observatory, partly sunk into the ground so that its instruments would be steadier and less troubled by wind. The instruments themselves were the largest and most carefully made in Europe. Quadrants and sextants and armillary spheres of brass and steel, some of them a good deal more than a meter in radius, with divided scales read by transversal marks that allowed fractions of a degree to be estimated. A great mural quadrant fixed to a wall along the meridian gave altitudes of objects as they crossed the north to south line. What mattered as much as the size of the instruments was the discipline that surrounded them. Tycho measured the same star with different devices and compared results, checked his scales for error and kept a record of those errors, made allowance for the bending of light in the atmosphere near the horizon, and had several observers watch the same event independently. The consequence was a catalogue of stellar positions and a running record of planetary places, good to something of the order of 1 or 2 minutes of arc, which is a small fraction of the apparent width of the full moon, and lies close to the practical limit of the unaided eye. Tycho himself did not accept the Copernican arrangement. He proposed instead a compromise in which the Earth stood still, the Sun circled it, and the other planets circled the Sun, a scheme geometrically equivalent to Copernicus in most respects while leaving the Earth at rest. He knew that his observations were the raw material from which a correct system could be extracted, and he also knew that the extraction would demand mathematical labor of a kind he had little appetite for. After a quarrel with the Danish court, he left the island, and by the end of the 1590s he had settled in Bohemia as imperial mathematician to Rudolf II, taking with him his records and his ambitions and the need for a competent calculator. Johannes Kepler had studied at Tübingen, where he learned the Copernican system from Michael Maestlin and became convinced of it, and in 1596 he published a small book arguing that the spacing of the planetary orbits reflected the nesting of the 5 regular solids. It was a speculation built on the best available numbers, and Kepler understood that testing it would require better ones. He was then teaching in Graz, and when religious pressure made his position there untenable, he traveled to Bohemia, where he joined Tycho in the year 1600. Their collaboration was uneasy, since Tycho released his observations sparingly and in small portions, and it was cut short when Tycho died in October of 1601. Kepler succeeded him in the imperial post, and the archive of observations came into his hands. The task assigned to him in the division of labor at Tycho's establishment had been Mars, and Mars was where the discrepancies were worst. There is a story, repeated by Kepler himself in a lighter passage, that he undertook to settle the orbit within a week or so. The work in fact occupied him for years, and he came to describe it as a campaign, a war conducted against a stubborn adversary. The conditions of the campaign were unusual in the history of the subject. He had roughly 2 decades of Mars positions of a quality that would expose any error greater than a few minutes of arc. He had a firm commitment to the idea that the Sun was the physical source of the planet's motion, and he had nothing but pen, paper, and tables of trigonometric functions with which to grind through the geometry. His first substantial result was a model of the traditional kind, a circular orbit with the Sun placed off-center and the uniform motion referred to yet another point, fitted with great care to a set of Mars oppositions. It reproduced the observed longitudes at opposition to within about 2 minutes of arc, which by any earlier standard was a triumph. Kepler then tested it where it had not been fitted, against positions away from opposition and against the planet's latitudes, and it failed. The failure was small. In the worst places, the model and the observations parted company by about 8 minutes of arc, roughly a quarter of the Moon's apparent diameter. Any earlier astronomer would have been entitled to ignore such a residue, and Kepler said as much, remarking that those 8 minutes, which he could not explain away because Tycho's work did not permit him to doubt them, obliged him to reform the whole of astronomy. Having rejected his own successful fit, he set about the problem from a different direction. He used the fact that Mars returns to the same point among the stars after an interval of about 687 days. so that observations separated by that interval, or by multiples of it, catch Mars in one fixed position while the Earth stands in different places. By triangulating from such pairs, he was able to determine the shape of the Earth's own orbit independently, and he found that the Earth, too, moves unevenly, faster when nearer the Sun and slower when further away, in a manner that could be expressed as a simple relation between speed and distance. From that relation, he developed the rule that the line joining planet to Sun sweeps out equal areas in equal times, a statement about how a planet moves along its path that he arrived at before he knew what the path was. The path resisted him. He was satisfied that the orbit was some closed oval, narrower than a circle and symmetrical about the line through the Sun, and he tried a succession of candidate ovals, calculating positions for each and comparing them with Tycho's figures. One family of curves left the planet lagging behind the observations, another pushed it ahead, and the errors of the two attempts were of similar size and opposite sign, which suggested that the true curve lay between them. The ellipse lay between them. Kepler had considered ellipses earlier and set them aside as too simple and too arbitrary. And when he came back to the ellipse, he found that a curve with the Sun at one of its two foci, taken together with the area rule, reproduced the observed positions of Mars within the accuracy of the observations themselves. The departure from circularity is not large. For Mars, the Sun sits away from the center of the ellipse by about 9/100ths of the longer radius, and the shorter radius of the figure is less than 1% smaller than the longer one, so that a drawing of the orbit at any ordinary scale looks circular to the eye. What betrayed it was the offset of the Sun and the varying speed, both amplified in the sky because Mars approaches relatively close to the Earth, and because the eccentricity of its orbit is greater than that of Venus, Jupiter, or Saturn. Kepler published the result in 1609, in a book on the motions of the star Mars, which set out not only the conclusions but the failed attempts in sequence, and a decade later he added the relation between orbital periods and orbital sizes that completed the set. The telescope reached Mars later than it reached the Moon, in the sense that it took decades before anyone could say with confidence what was being seen. Galileo turned his instruments on the planet in the years after 1610 and reported that Mars did not appear perfectly circular to him, and he had expected as much, since a body orbiting beyond the Earth and lit from the Sun should show a slight gibbous shortfall when it stands away from opposition. The effect is real, and it amounts at most to a modest flattening of one edge of the disk, but it lies close to the limit of what his small lenses could deliver, and he wrote with unusual caution about it. The planet remained in those first years a point that had swollen into a small round patch of light. Part of the difficulty was simply size. Even at its closest, Mars presents a disk about 25 seconds of arc across, which is roughly 1/70th of the apparent width of the Moon, and at the less favorable oppositions, the figure falls to about 14 seconds. The oppositions themselves come round only about every 2 years and 2 months, and the close ones, when Mars arrives at opposition near the part of its orbit closest to the Sun, are separated by 15 or 17 years. An observer, therefore, had a few weeks of useful nights, followed by a long wait, and had to hope that the air over the observatory would be steady during those weeks, rather than rippling the image into an unreadable smear. The instruments added their own troubles. The early refractors used single lenses of ordinary glass, which bring different colors to focus at different distances and surround every bright object with a fringe of violet and yellow, and the standard remedy was to make the focal length very long so that the color error, spread over a great distance, became less obtrusive. Tubes of 10, 20, and eventually more than 30 feet were used, sometimes with the lens mounted on a mast and the eyepiece held below on a frame. The images were dim, the mountings awkward, and the magnifications that the optics could honestly bear were modest. Marks on the disk of Mars sat at the edge of what such an arrangement could show. Francesco Fontana, working in Naples in the 1630s, published drawings of Mars that show a round disk with a dark blot at its center and a dark rim around its edge. Neither feature corresponds to anything on the planet. The central blot is the signature of a defect in his lens, and it appears in his drawings of other bodies as well, which is how it was later recognized for what it was. The drawings are still of some interest, because they mark the beginning of the habit of recording what the disk looked like rather than merely where it was, and because they show how difficult it was before anyone had a reliable image to compare against, to separate the planet from the instrument. The first drawing that can be matched to a real feature was made by Christian Huygens on the 28th of November, 1659. It shows a large dark wedge occupying much of the disk, broad at the top and tapering downward, and the shape corresponds to the region now called Syrtis Major, the darkest and most consistently visible marking on the planet. Huygens watched it on subsequent nights, saw that it moved across the face and returned, and concluded that Mars turns on its axis in something close to 24 hours. That estimate was rough, and it was arrived at from a handful of sketches made by eye, but the general result was sound and it has never been overturned. The Martian day is close to our own. Huygens returned to Mars at later oppositions, and in 1672 he recorded a bright spot at the southern limb of the disk, drawn as a small white patch set into the edge of the sphere. This is the earliest clear notice of a polar cap, and Huygens made no strong claim about what it was. It was simply a whiteness where the rest of the disk was ruddy or grey, sitting near the end of the axis about which the markings appeared to turn. Giovanni Domenico Cassini, observing from Bologna in 1666 and afterwards from Paris, took the timing of the rotation further. By watching a particular dark marking cross the central line of the disk, and noting the clock time, then repeating the observation night after night, he arrived at a period of 24 hours and 40 minutes. The modern value is 24 hours, 37 minutes, and about 22 seconds. So Cassini was within a few minutes of the truth using a pendulum clock and a long refractor. He also saw the polar whiteness, and he noticed something that would occupy his successors, that the markings did not always look the same from one apparition to the next. The reason the rotation period was hard to pin down, and the reason it could eventually be pinned down very precisely, lies in the same arithmetic. Because the Martian day is about 37 minutes longer than the Earth's, an observer who looks at the planet at the same hour each night sees the markings displaced a little westward each time, and after about 40 nights, the accumulated displacement amounts to a full turn, and the disk looks as it did at the start. An observer who compares two drawings separated by a few weeks can therefore be wrong by a whole rotation without noticing. An observer who compares drawings separated by years and who has counted the intervening rotations correctly divides a very long interval by a very large number and obtains a period good to seconds. That is how later determinations were made, using Huygens and Cassini's sketches as the earliest fixed points in a chain. The opposition of 1672 served another purpose entirely. Jean Richet traveled to Cayenne on the northern coast of South America and observed the position of Mars against nearby faint stars, while Cassini did the same from Paris, the intention being to detect the small shift of the planet's apparent place that arises from viewing it from two widely separated points on the Earth. From that shift, combined with the known ratios of the planetary distances, a value for the distance of the Sun could be derived. The number they obtained was somewhat too small, but it was of the right order, and it was the first measurement to put the scale of the solar system into the range we now accept. Mars, being both nearby and reliably locatable against the stars, was the natural planet to use. Giacomo Filippo Maraldi, a nephew of Cassini who worked in Paris, watched Mars through the oppositions of the early 1700s and again in 1719, and he was the first to follow the polar caps with any persistence. He recorded that the southern cap changed in size over the weeks of an apparition, growing at some times and shrinking at others, and he noticed that it was not quite centered on the point about which the markings appeared to pivot, so that it seemed to swing slightly as the planet turned. He also confirmed that the dark markings, while broadly repeating, altered in outline and darkness from one year to another. His estimates of the rotation period agreed closely with Cassini's. William Herschel brought reflectors of his own making to the problem in the 1770s and 80s, and their apertures were larger than anything used on Mars before, which allowed higher magnifications on the nights when the air permitted. Working chiefly through the oppositions of 1777, 1779, 1781, and 1783, he tracked the drift of the markings carefully enough to fix the direction in space of the axis of rotation, and he found that the axis is tilted from the perpendicular to the orbit by something in the region of 30 degrees. The modern figure is a little over 25 degrees, so his value was too large. But the conclusion that mattered was correct. Mars is tilted much as the Earth is, and it therefore has seasons of the same kind, longer in proportion to its longer year. Herschel then connected the seasons to the caps. He watched a cap grow through the winter of its own hemisphere and diminish through the summer, and he watched the two caps behave in opposition to one another, one advancing as the other retreated, which is exactly what a seasonal deposit of something white and volatile would do. He took them to be accumulations of snow and ice. He also tried to gauge the planet's air by watching Mars pass close to faint stars, reasoning that a substantial atmosphere would dim a star seen through its outer layers, and, finding no clear dimming, he nonetheless concluded that Mars possessed a considerable atmosphere. His measurements of the disk gave a globe roughly half the diameter of the Earth, and he suspected a slight polar flattening, though the amount he assigned to it was too great to be real. The 19th century inherited from Herschel a planet with a known spin, a known tilt, seasonal caps, and a set of vague dark patches, and it set about the slow business of turning those patches into a map. The work was governed by a rhythm no observer could hurry. Mars and the Earth come into line with the Sun a little more than every 2 years. at intervals averaging about 780 days, and only near those oppositions does Mars stand high in the night sky with its full disk turned towards us. Even then, the disk is small, reaching at best something under 26 seconds of arc, and at unfavorable oppositions barely half of that, because the orbit of Mars is decidedly eccentric, and the distance at closest approach varies a great deal from one meeting to the next. The best oppositions, when Mars is near the perihelion of its own orbit, come round in a longer cycle of roughly 15 to 17 years, and 19th century observers planned their careers around them. The first serious cartography came from a private observatory in Berlin belonging to a banker named Wilhelm Baer, who worked in partnership with the astronomer Johann Heinrich Mädler. Their instrument was a small refractor by Fraunhofer with an aperture of about 9.5 centimeters, modest even by the standards of the day. But it was well figured, and they used it with unusual discipline. Through the oppositions of the 1830s, they drew the disk repeatedly, always at the same scale, and rather than sketching whatever caught the eye, they recorded the same features again and again, timing the moments when a marking crossed the center of the disk, so that its longitude could be derived from the rotation of the planet. From these timings, they refined the rotation period to within a fraction of a second of the modern value, and in 1840 they published the first true map of Mars, a pair of small hemispheres showing the principal dark regions in their relative places. The map was crude by any later standard, and it contained no names, only letters and a few numbered points. But it settled something important. The markings held their positions from one opposition to the next across years, which meant they belonged to a solid surface and not to a shifting cloud deck of the sort that dominates Jupiter. Beer and Mädler also chose a small dark marking near the equator as their reference for zero longitude, and a version of that choice has persisted since the modern prime meridian of Mars lies in the same region, in what Schiaparelli would later call Sinus Meridiani. The two men produced their Mars work almost as an aside to their much larger survey of the Moon, and the same habits of patient repetition and honest omission served them in both. Through the middle decades of the century, the drawings multiplied and improved as apertures grew. In England, William Rutter Dawes, who had a reputation for exceptionally fine eyesight and an 8-inch refractor to use it with, made a series of drawings in the mid-1860s that showed the shapes of the dark regions with a clarity nobody had reached before, including the broad wedge that would come to be called Syrtis Major and the ragged coastlines flanking it. In Italy, Angelo Secchi observed Mars from Rome and applied to one dark streak the word canale, which in Italian means a channel or a strait, and carries none of the implication of excavation that its English cousin does. At Leiden, Frederick Kaiser gathered old and new observations together and improved the rotation period further. In England again, Richard Proctor compiled the drawings into charts and proposed a system of names that honored the observers themselves, so that his maps carried a Dawes Ocean, a Herschel Strait, a Mädler Continent, a Kaiser Sea. Nathaniel Green, a painter as well as an astronomer, took a telescope to Madeira for the steadier air and produced a set of colored drawings of considerable delicacy. The names reflected an interpretation that seemed natural at the time, The dark areas were taken for water and the lighter ochre expanses for land, so the vocabulary of terrestrial geography was applied without much hesitation. Seas, straits, bays, continents, islands. There were reasons for the reading. The dark regions were broad and bounded. They showed something like coastlines, and they were greyish or greenish against the ruddy background. There were also difficulties which the more careful observers noticed. The dark regions changed shape and depth of tone with the Martian seasons, darkening in a wave that seemed to spread from the melting polar cap towards the equator, and standing water would not behave that way. Occasionally, a marking could be traced faintly across what was supposed to be open sea. Some observers began to suspect vegetation instead, or damp ground, or drifting dust, and the debate over what the tones meant would outlast the century. None of this was easy work, and it is worth being plain about the conditions. An observer at the eyepiece sees a small bright disk trembling and boiling in the Earth's atmosphere, sharp for a second or two and then smeared for a minute, and the details on it are faint contrasts rather than hard edges. There were no photographs of any use for surface detail until much later, so the record was made by hand and by memory, one glimpse at a time, and each drawing was the residue of 100 fragmentary impressions filtered through one person's eye, expectations and drawing skill. Different observers looking at the same face of Mars on the same night produced charts that agreed in their broad masses and disagreed in almost every detail. The eye, working at the limit of what it can resolve, tends to organize scattered faint patches into continuous forms, and the hand tends to draw what the mind has organized. Into this situation came Giovanni Schiaparelli, director of the Brera Observatory in Milan, who turned to Mars at the favorable opposition of 1877 with a Merz refractor of about 22 centimeters aperture. He approached the planet as a positional astronomer rather than as an artist, measuring the coordinates of hundreds of points with a micrometer and building his map from the measurements outward, rather than sketching an impression and fitting coordinates to it afterwards. He also swept away Proctor's nomenclature and replaced it with one drawn from the geography and mythology of the ancient Mediterranean and the classical imagination, so that the map of Mars acquired a Mare Erythraeum, a Syrtis Major, a Hellas, an Elysium, a Utopia, a Solis Lacus, a Margaritifer Sinus, an Arcadia, an Amazonis, a Tharsis. The names were sonorous, neutral as to who had discovered what, and they took hold. A great many of them survive on the maps made from spacecraft imagery, attached now to volcanic plateaus, impact basins and dust-covered plains rather than to seas and lands. Among the features Schiaparelli recorded and named were fine linear markings crossing the bright regions, which he called canali in Secchi's sense of channels. That same opposition, in the early autumn of 1877, brought Mars to within about 56 million kilometers of the Earth, among the closest approaches of the century. At the United States Naval Observatory in Washington, Asaph Hall had the use of a refractor of 26 inches aperture made by Alvan Clark and Sons, then the largest refractor in the world, and he decided to use the close approach to search for satellites. The search was awkward because the glare of the planet itself drowned anything faint nearby, so he worked with the bright disk pushed just outside the field of view and swept the space around it. In the middle of August, he glimpsed a faint point of light, lost it to bad weather, recovered it days later, and then found a second, nearer object. The outer moon he had seen first, the inner one followed. On the suggestion of an English schoolmaster, they were named Phobos and Deimos, after the attendants of Ares in the Iliad. Their orbits were remarkable in a quiet way. Deimos circles Mars in about 30 hours, a little longer than the Martian day, while Phobos completes a circuit in under 8 hours, which is much shorter than the day, so that seen from the surface it would rise in the west, cross the sky, and set in the east, twice within a single Martian night and day. Both are small, mere tens of kilometers across, and in 1877 nothing could be known of their shape. What their discovery did give immediately was an accurate mass for Mars, since the period and distance of a satellite yield the mass of the body it orbits, and the figure that emerged was close to 1/10 of the mass of the Earth. Hall's wife, Angeline Stickney, is remembered in the name of the great crater that dominates one end of Phobos. The same opposition that gave Asaph Hall his 2 moons gave Giovanni Schiaparelli, in Milan, the finest view of Mars he had ever had. He was then the director of the Brera Observatory, working with a refractor of about 8 3/4 inches aperture made by the Munich firm of Merz. A modest instrument by the standards of Washington or Mount Hamilton, but placed under skies that on certain nights held remarkably still. Schiaparelli had trained as an engineer before turning to astronomy, and he brought to the eyepiece the habits of a surveyor. He measured positions of features rather than sketching impressions of them. He built up his map from repeated determinations, and he distrusted anything he could not fix with coordinates. Over that autumn, he recorded the familiar dark regions that earlier observers had charted, and among them he traced a network of narrow, nearly straight markings running from one dark area to another, faint and hard, he said, at the very limit of what the telescope would show. He called them canali, which in Italian carries the ordinary sense of a channel, a groove, a natural watercourse, without any implication that something had dug it. For the whole map, he devised a nomenclature drawn from classical geography and myth, giving the dark patches names of seas and bays, and the bright regions names of lands, and giving the linear features the names of rivers, real and legendary: Nilus, Ganges, Hydaspes, Phaison, Euphrates. It was a beautiful and orderly system, and it displaced the older English names almost completely, so that the vocabulary of Martian geography became Latin. Into English, however, canali passed as canals, a word which in the 1870s belonged to engineering, to Suez and to the great works of inland navigation, and the translation did a good deal of the argument's work before the argument had properly begun. Not everyone drew the planet the way Schiaparelli drew it. During the same close approach, the English observer Nathaniel Green watched Mars from Madeira, choosing the island for its steady air, and he was a painter by training as well as an astronomer. His map showed soft, graded shading, patches whose edges dissolved, tones that ran into one another without boundaries, and when the 2 maps were compared, it was clear that the same planet had produced 2 different kinds of picture. Green thought Schiaparelli had hardened diffuse markings into lines and said so with courtesy. Schiaparelli thought Green had blurred real detail. There was no way to settle the disagreement except by more observing, and more observing produced more of both kinds of drawing. Schiaparelli continued through the oppositions of the 1880s, eventually with a larger refractor at Brera, and his network grew denser. In 1882, he described something stranger still, which he called gemination. Certain of the lines appeared, on some nights and not others, to be doubled, two fine parallel streaks separated by a narrow bright interval, as though a single channel had split lengthwise. He was cautious about it and puzzled by it, and he never claimed to understand it. Then in 1886 at Nice, Henri Perrotin and Louis Tolon turned the 30-inch refractor of that observatory towards Mars and reported that they too could see the lines. That mattered a great deal, because Nice had one of the largest telescopes in the world and no stake in the Milanese map. And after their announcement, the canals ceased to be one man's peculiarity and became a subject in the literature. The question of what they were was answered most confidently by an American who came to the problem late and from outside the profession. Percival Lowell belonged to a wealthy Boston family, had traveled in Japan and written about it, and had the means to build an observatory wherever he chose. He chose Flagstaff in the Arizona Territory at an elevation of about 7,000 feet, on the reasoning that height and dryness would give steadier images than the lowland observatories of the East. And he began observing Mars there in the favorable opposition of 1894 with borrowed refractors before installing a 24-inch Clark. His conclusions were published within a year in a book called simply Mars and elaborated in two more over the following decade. Lowell's Mars was an old planet, smaller than the Earth and further from the Sun, which had lost most of its water and most of its air, and whose remaining moisture was locked up seasonally in the polar caps. On such a world, he argued, agriculture would be possible only where water was brought deliberately from the poles to the temperate latitudes, and the network he traced was the visible sign of that undertaking. He did not claim to see the waterways themselves, which would be far too narrow for any telescope. He supposed that each line was a broad band of irrigated ground flanking a channel, vegetation darkening the desert along its course. Where the lines crossed, he drew small round spots and called them oases. He mapped hundreds of these features, published catalogues of them, and noticed that they appeared to darken in a wave that spread from the melting cap towards the equator as the Martian spring advanced. The scheme was coherent, it explained the geometry, and it was written with great fluency for a general readership, which is why it took hold in the newspapers and the popular imagination far more firmly than in the observatories. Because inside the observatories, doubt was accumulating. Edward Emerson Barnard, using the 36-inch refractor at Lick, larger than anything at Flagstaff, saw abundant detail on Mars in the middle 1890s and saw it as irregular, blotched and broken, with nothing he was willing to call a straight line. Vincenzo Cerulli, observing from his private observatory at Colurania in Italy, reached a conclusion that turned out to be the important one. On the rare nights when the air was quietest, the lines he had drawn before came apart into a scatter of small, disconnected markings, and he suggested that the whole network was an artifact of the eye assembling detail it could not properly resolve. Eugène Antoniadi, who had learned the planet under Camille Flammarion, was given the use of the great refractor at Meudon of about 33 inches aperture for the opposition of 1909, and reported the same thing more decisively. He found the disk covered with irregular mottling, complex, shaded, patchy, entirely without geometry, and he said afterwards that the canals had never existed, that they were the summary a strained eye makes of detail beyond its reach. The argument was also pursued away from the telescope. In 1903, Walter Maunder and Joseph Evans arranged a test at the Royal Hospital School at Greenwich, in which schoolboys were seated at a distance and asked to copy a disc bearing irregular smudges and dots, with no knowledge of what the exercise was for. A number of the drawings came back with the markings joined into fine straight lines. The tendency was not confined to children or to amateurs. It appeared to be a general property of vision, working at the threshold of resolution, where the eye completes and regularizes what it half sees, particularly during the long minutes of drawing at an eyepiece with a shifting, boiling image and a memory of what was there a moment ago. Alfred Russel Wallace, in a short book published in 1907, attacked the scheme from another direction, arguing on physical grounds that Mars was far too cold and its atmosphere far too thin for open channels of liquid water to serve any purpose at all, and that the engineering Lowell described would have been futile even for engineers. The controversy did not end in a single moment. It thinned out. Observers with large apertures and steady air kept failing to see lines. The physical measurements of temperature and water vapor kept coming back unfavorable, and the men most committed to the canals grew old. Lowell died in 1916 with his interpretation intact, and Flagstaff turned to other work. Antoniadi's account of the planet, published in 1930, became the standard one, and it described a mottled surface with seasonal shading and no artificial features. What lingered longest was the vocabulary, since the maps kept the Latin names of the seas and lands for decades. And the darkening wave kept a place in the textbooks until it was explained as the movement of dust. The episode left a clear lesson about the limits of the method that had produced it. At the edge of resolution, a careful and honest observer can draw, in perfect good faith, something that is not there. The argument over what could be seen on Mars had exhausted itself, and while it was still running its course, a different way of working had been quietly gathering strength. One that did not depend on the steadiness of a night or the honesty of a hand at the eyepiece. Light arriving from Mars carries more than a shape. Spread out by a prism or a grating, it shows dark absorption lines where gases along its path have removed particular wavelengths. Gathered onto a sensitive junction of two metals, it can be weighed as heat. Examined for the direction in which its waves vibrate, it reports on the texture of the grains that last reflected it. None of these measurements produced a picture, and none of them settled anything quickly, but each of them could, in principle, be repeated by another observer with another instrument, and disagreement between them could be traced to something other than temperament. The spectroscope was turned on Mars early. In the 1860s, William Huggins compared the spectrum of the planet with that of the Moon, on the reasonable assumption that the Moon, being airless, offered a control and reported absorption features that he attributed to water vapor in the Martian air. The comparison was harder than it looked. Any light from any object beyond the Earth reaches the observer only after passing through many kilometers of the Earth's own atmosphere, which is thick with water vapor and oxygen, and the lines those gases impress on the spectrum sit at exactly the wavelengths one wishes to examine on Mars. Later observers with better instruments could not confirm the detection. William Wallace Campbell, working at the Lick Observatory in the 1890s, found the spectra of Mars and the Moon to be alike within the precision he could achieve, and concluded that whatever water vapor Mars possessed was too little to register. When Vesto Slipher at Flagstaff photographed Martian spectra in the first decade of the new century, and Lowell announced that water vapor had been found, Campbell took a spectrograph to the summit of Mount Whitney, above much of the terrestrial vapor, and again saw nothing that required Martian water. The way out of this difficulty was already understood in principle and took decades to realize in practice. Mars moves relative to the Earth, and its light is therefore shifted slightly in wavelength by the Doppler effect, by an amount that depends on how fast the two planets are separating or approaching. At the right time in the planet's cycle of oppositions, the shift is large enough that a Martian absorption line will sit a little to one side of the corresponding terrestrial line rather than hiding beneath it. Exploiting that separation demanded a spectrograph of high dispersion, a large telescope to feed it, and photographic emulsions sensitive in the deep red and near infrared, where the useful bands of water and carbon dioxide lie. Through the 1930s, Walter Adams and Theodore Dunham at Mount Wilson pushed at the problem, and their results were negative in a useful way. They set upper limits, and the limits were low. Oxygen, if present at all, amounted to a small fraction of the terrestrial quantity. Water vapor remained undetected. While the spectroscopists were failing to find water, other instruments were measuring warmth. A thermocouple generates a small voltage when one of its junctions is heated, and by the 1920s, such devices could be built sensitive enough to register the trickle of infrared radiation that a planet's disk delivers to a large mirror. William Koblentz of the National Bureau of Standards worked with Carl Lampland at the Lowell Observatory, and Edison Pettit and Seth Nicholson worked at Mount Wilson, and both groups scanned across the image of Mars, sampling the center of the disk, the limb, the poles, and the dark regions separately. The numbers they obtained agreed in their general shape. Near the point where the sun stood overhead, on a summer afternoon in the Martian tropics, the ground could rise to something around the freezing point of water, or a little above it. Away from that point, the temperature fell steeply, so that the morning and evening limbs were far colder than the middle of the day, and the polar regions were colder still, well below anything terrestrial experience offers outside the ice sheets. The variation across a single day was much larger than on Earth. That steep swing was itself a measurement of the atmosphere. A thick blanket of gas moves heat about, holds some of it through the night, and keeps the day and the night from diverging too far. A very thin one does almost none of this, and the surface then follows the sun closely, heating quickly and cooling quickly. The Martian numbers pointed to a thin, dry atmosphere over a poorly conducting ground, most likely a fine dust or a granular soil, which lost its heat within an hour or two of sunset. The dark markings turned out to be slightly warmer than the bright ones, which is what a darker surface should be, and offered no support for any interpretation more elaborate than a difference in albedo. Polarimetry came at the surface from another side. Bernard Liot at Meudon had developed instruments capable of measuring the small degree to which reflected light becomes polarized, and had built up curves for terrestrial substances, showing how the polarization varies with the angle between the sun, the object, and the observer. Audouin Dollfus continued this work over many years. comparing the curves obtained from Mars with those measured in the laboratory from powders, crushed rocks, volcanic ash, and iron-bearing minerals, ground to different degrees of fineness. The Martian bright regions matched fine pulverized material rather than solid rock or vegetation, and the reddish color was consistent with oxidized iron distributed through that dust. The same technique registered occasional hazes and clouds in the atmosphere, whose polarization differed from the ground beneath them, which gave a way of following the veils and the seasonal brightenings without having to decide what they looked like. Carbon dioxide entered the account in 1947, when Gerard Kuiper obtained infrared spectra of Mars with the Large Reflector at the McDonald Observatory and found the absorption bands of carbon dioxide clearly present, stronger than the corresponding bands in the spectrum of the Moon, and therefore Martian rather than terrestrial in origin. The quantity implied was modest in absolute terms, but larger per unit of atmosphere than the trace of carbon dioxide in the air of the Earth. Kuiper also looked for the absorption that chlorophyll imposes on reflected light and did not find it in the dark regions, which removed one long-standing reason for thinking of them as vegetated. Water vapor was finally detected in 1963 when Hiron Spinrad, Guido Munch, and Lewis Kaplan examined high-dispersion spectra taken at Mount Wilson and identified faint Martian lines displaced by the planet's motion from their terrestrial counterparts. The amount was very small. Condensed onto the surface, the entire column of vapor above a given place would have made a film of water a small fraction of 1/10 of a millimeter deep, which is less than the driest desert air on Earth contains. The same spectra carried a second piece of information because the shape and strength of the carbon dioxide bands depend on the pressure of the gas doing the absorbing, and the analysis pointed to a surface pressure of a few tens of millibars at most, considerably lower than the figure of roughly 1/10 of the terrestrial value that had been carried in textbooks for a generation on the strength of estimates from atmospheric scattering. Later measurements would lower it further. Radio astronomy added its own line of evidence. Mars emits T at centimeter wavelengths, and because such radiation escapes from some depth below the surface rather than from the surface itself, the brightness temperatures measured with radio telescopes described the subsoil steadier than the ground above it and cold. In the early 1960s, radar transmitters became powerful enough to send a signal to Mars and receive the echo, and the returned pulses, spread in time and in frequency by the roughness and rotation of the reflecting surface, gave the first crude measures of Martian relief and of how rough the ground was at the scale of the wavelength used. By the middle of that decade, Robert Layton and Bruce Murray, calculating how heat would flow into and out of such a surface under such an atmosphere, argued that the winter pole would grow cold enough to freeze carbon dioxide directly out of the air, so that the caps were, at least in part, not water frost at all, but a seasonal condensation of the atmosphere itself. The exploration of Mars by spacecraft began, as most such beginnings do, with a series of failures that left little trace in the public memory. The Soviet Union had been sending probes toward the planet since the early 1960s, and one of them, Mars 1, launched in 1962, fell silent months before it reached the vicinity of its target, so that whatever it might have measured was never returned. In the United States, the two spacecraft prepared for the 1964 launch opportunity were built as a pair. on the reasonable assumption that one of them would not survive the journey. The first, Mariner 3, lifted off in early November of that year, but the shroud that protected it during ascent failed to separate. The solar panels could not open, and the batteries ran down within hours. Engineers had a matter of weeks to design and fit a new shroud before the launch window closed. Mariner 4 left Cape Kennedy on the 28th of November, 1964, atop an Atlas rocket with an Agena upper stage, and this time everything unfolded as intended. The spacecraft weighed a little over 260 kilograms and carried a modest set of instruments, among them a magnetometer, detectors for charged particles and cosmic dust, and a single television camera mounted on a scan platform. The camera was a small and slow device by any later standard. It produced pictures of 200 lines, each line resolved into 200 elements, with each element assigned one of 64 levels of grey, and the whole image was recorded not on film, but as a string of digits written onto a loop of magnetic tape. The radio link back to Earth could carry only about 8 bits every second, which meant that a single frame took hours to transmit, and the full sequence took days. The team accepted this because the alternative, sending pictures in real time, was beyond the capability of the transmitter and the antennas then available. The journey lasted nearly 8 months. On the 14th and 15th of July 1965, Mariner 4 passed within roughly 10,000 kilometers of the Martian surface, its camera taking a sequence of frames along a swath that ran from the northern limb southeastward across bright and dark regions toward the evening terminator. And then, its imaging done, the spacecraft continued behind the planet as seen from Earth, so that its radio signal grazed the atmosphere on the way in and again on the way out. That last maneuver was not incidental. The bending and weakening of a radio beam as it passes through a gas depends on the density of that gas, and the occultation experiment was designed to convert those changes into a profile of the atmosphere and a value for the pressure at the ground. The pictures came back slowly as strings of numbers, and while the image processing equipment was still working on the first frame, members of the staff at the Jet Propulsion Laboratory taped the printed numerical strips to a wall and colored them by hand with pastels bought from an art shop, assigning a shade to each range of brightness so that the earliest human view of Mars from close range was a piece of colored paper hanging in a corridor. It showed the curve of the limb against black sky and very little else. The next several frames showed a surface that was difficult to interpret, hazy and low in contrast. Then, in the 7th frame, there appeared a large circular depression with a raised rim and a clearly shadowed interior, and in the frames that followed, there were more of them, dozens in total, ranging from a few kilometers across to well over 100, crowded together in places and overlapping one another in the way that craters do on the Moon. 21 complete frames and a fragment of a 22nd were returned, and every one of them was transmitted twice to guard against errors. The total coverage amounted to roughly 1% of the surface of the planet, in a narrow strip at a resolution that could not resolve anything smaller than a few kilometers. Within those limits, the conclusions were reasonably firm. The cratered ground was old because craters accumulate over time and are erased by wind, water, volcanism, and the movement of crust, and a surface as heavily marked as this one had evidently escaped all of those processes for a very long time. There was no sign of the linear features that had been drawn and argued over for 70 years, and no visible difference in relief between the bright regions and the dark ones the strip had crossed, which suggested that the classical markings were differences of surface material rather than of elevation or of vegetation. The occultation gave a surface pressure of only about 5 millibars, less than 1/100th of the pressure at sea level on Earth, and considerably lower even than the reduced figures the spectroscopists had begun to converge on. An atmosphere that thin cannot support liquid water at the surface for any length of time, since water exposed to such low pressure boils away at temperatures well below its ordinary boiling point. And it also offers very little shielding against ultraviolet light or against the impact of small meteoroids, which is part of why the craters had survived. The magnetometer found no magnetic field of any consequence, and the particle detectors found no trapped radiation belts, so the planet had neither the internal dynamo nor the magnetic cavity that protects the Earth from the solar wind. Mariner 4 itself continued to work for another 2.5 years, returning data on the interplanetary medium until contact was ended in December of 1967. The result was widely reported as the discovery of a dead world, and although that phrase carried more finality than the evidence deserved, given how small a fraction of Mars had been seen, it did describe the shift in expectation accurately enough. The lingering hope of a habitable planet with a thin but breathable air, seasonal vegetation and channels of some kind did not survive the combination of 5 millibars, no magnetic field, and a surface that looked lunar. The next opportunity came in 1969, and the two spacecraft sent to use it, Mariner 6 and Mariner 7, were built to a different scale. They launched in February and March of that year on Atlas Centaur rockets, arrived at the end of July and the beginning of August, passed within about 3,500 kilometers of the surface, and carried 2 cameras each, one wide angle and one narrow, together with an infrared radiometer, an infrared spectrometer, and an ultraviolet spectrometer. Their radio links could carry data thousands of times faster than Mariner 4's, and between them they returned something on the order of 200 pictures, some taken from a distance during the approach, which allowed whole hemispheres to be seen turning, and some taken close in during the few minutes of encounter. Mariner 7 suffered a serious fault on the way, losing contact and showing signs of a damaged battery, and after it was recovered, its trajectory and its instrument sequence were adjusted so that it could examine the southern polar cap. The infrared radiometer measured a temperature over the cap of around -123 degrees Celsius, which is close to the temperature at which carbon dioxide condenses at Martian pressures, and that measurement effectively confirmed what had been argued from theory a few years earlier, that the seasonal caps are frozen atmosphere rather than snow of water. The spectrometers found carbon dioxide dominating the air, along with traces of carbon monoxide, and in the upper atmosphere, atomic hydrogen and oxygen escaping into space. Further occultation measurements refined the surface pressure and showed that it varied from place to place by enough to indicate differences of several kilometers in elevation. The pictures again showed craters in abundance, but they also showed terrain that did not resemble the Moon. The Great Basin of Hellas appeared almost blank, without craters of any size, as though something had filled or scoured it. Elsewhere, there were regions of collapsed and jumbled ground, short ridges and irregular blocks in disordered arrangement, which the imaging team called chaotic terrain for want of any known analogue. And once more, no canals. The straight lines had no counterpart at any scale the cameras could see. What the Flybys did not do was sample the planet evenly. 3 narrow strips and a set of distant views cannot represent a world, and by an accident of timing and trajectory, the regions photographed in 1965 and 1969 excluded the highest ground and the deepest gash on Mars, so that a planet with volcanoes larger than any on Earth was described in the literature of the late 1960s as an old, cold, cratered body on which very little had ever happened. The plan had not been for 1 spacecraft, but for 2. In the launch window of 1971, the United States prepared a pair of orbiters, identical in design and complementary in assignment. The first to survey the planet broadly at moderate resolution, and the second to return to selected places and watch how they changed with time. The first of the pair was lost minutes after leaving the ground when its upper stage failed, and it fell into the Atlantic, so that the whole of the mission, both halves of a divided task, passed to the second vehicle, which left Earth at the end of May and spent the following months crossing the gap between the 2 orbits, while its controllers rewrote the observing sequences to cover as much of the abandoned assignment as a single spacecraft could manage. While it was in transit, observers on Earth watched a bright patch appear in the southern hemisphere of Mars and spread. Dust storms had been recorded from the ground for decades, most often near perihelion, when the planet receives its greatest share of sunlight and the temperature differences that drive its winds are at their sharpest. And most of those storms had stayed regional and faded within weeks. This one did not. Through October, the obscuration widened until the familiar dark markings, the ones that had been sketched and mapped and argued over for a century, were gone from the telescopes of Earth. And the planet showed a nearly uniform ochre disk, with only the south polar cap standing out. The spacecraft arrived in the middle of November and fired its engine for about a quarter of an hour, slowing enough to be captured, and so became the first machine built on Earth to enter orbit around another planet. Its path carried it around Mars roughly twice a day, rising far from the planet and then dropping to within about 1,400 kilometers of the surface, inclined steeply enough to bring most latitudes eventually into view. The cameras opened. What they returned was a bland, low-contrast haze in which almost nothing could be measured, because the atmosphere between the lens and the ground was full of suspended dust that scattered light in every direction and flattened every shadow. 2 Soviet spacecraft reached Mars within weeks of the American orbiter and met the same conditions, and their descent capsules and imaging attempts yielded very little, one of them transmitting from the surface for only a matter of seconds. The American mission had an advantage that mattered more than any instrument. It was in orbit, it had propellant and power, and it could wait. Its controllers deferred the mapping sequences, spent the interval calibrating, watching the storm from above and photographing the 2 small moons, and let the planet settle. Over November and December, the dust slowly rained out of the air, as it must, and the surface began to emerge from the top down. Even at the height of the obscuration, a few features had shown through. 4 dark spots stood in the murk, spaced across a region of the Western Hemisphere long known to ground observers as a bright area called Tharsis. 3 of them arranged in a line running from northeast to southwest, and the fourth set apart to the northwest. Each spot had at its center a small circular hollow. As the atmosphere cleared, the spots resolved into the summits of enormous mountains, and the hollows into their summit craters, and the reason they had been visible during the storm became a simple matter of altitude. They stood above most of the dust. The largest of them coincided with a bright marking that 19th century mappers had recorded and named for the snows of Olympus, a spot that had puzzled observers because it sometimes brightened and sometimes did not. It proved to be a volcano some 500 kilometers or more across at its base, ringed by an outward-facing scarp, with a complex of overlapping collapse craters at the top, and rising to something in the region of 20 kilometers above the surrounding plains, which is more than twice the height of the greatest volcanic pile on Earth, measured from the sea floor. Its slopes were gentle, a few degrees at most, the profile of a shield built by fluid lava spreading in long, thin flows rather than by explosive eruption, and its flanks were covered in overlapping lobes and channels and low ridges that recorded episode after episode of that spreading. The three aligned spots to the southeast were volcanoes of the same family, smaller but still immense, standing along the crest of a broad regional rise that the mapping later showed to be a bulge in the crust thousands of kilometers wide. Running east from that bulge, near the equator, the cameras found a system of connected troughs that extended for roughly 4,000 kilometers, a fifth of the way around the planet, reaching depths of several kilometers and, in its central section, widths of well over 100. It had shown up in earlier telescopic maps only as a vague dark streak given a classical name, and no flyby strip had crossed it. Nothing on Earth is quite like it in scale. The canyon system was later named for the spacecraft that revealed it. The troughs are not the work of a river. Their walls are steep and terraced, and show layer upon layer of rock stacked to their full depth. Their floors hold dunes and landslide debris and, in places, their own thick sequences of layered material. And along much of the length the pattern is one of parallel faulting and collapse. Ground pulled apart and dropped as the Tharsis region rose. Short branching side canyons cut back into the plateau in blunt theater-headed forms, rather than tapering upstream as the valleys of rainfall do, and the imaging team read them as the signature of ground undermined by the removal of material from below, most plausibly water or ice, with the surface collapsing after it. Elsewhere, the same cameras found channels that did look like the beds of flowing water. Some were narrow and sinuous and fed by fine tributary networks in the old cratered uplands, resembling terrestrial drainage in miniature. Others were far larger, 100 kilometers wide in places, beginning abruptly in the disordered ground that the earlier flybys had photographed and named chaotic terrain, and running downhill for hundreds of kilometers with braided courses, streamlined islands shaped like teardrops around obstacles, longitudinal grooves and terraces along their inner banks. These were dry and had been dry for a very long time, since craters lay across their floors. Under the present atmosphere, thin and cold, liquid water cannot persist in the open. It would boil and freeze at once. The channels therefore implied either a different past climate or great releases of water from beneath the ground, or both, and the question of which was left open, as it remains open in part today. But the fact of the channels themselves was no longer in doubt. At the poles, the spacecraft found terrain unlike anything at lower latitudes. Broad plateaus of pale material cut by curving troughs and scarps, and in the walls of those scarps, fine alternating layers, dozens of them stacked in sequence. The reading offered then, and confirmed since, was that these are deposits of ice and dust laid down over long spans of time. They're layering a record of changes in the amount of sunlight the poles receive as the planet's spin axis and orbit slowly shift. By the time its attitude control gas was exhausted, in the autumn of 1972, the orbiter had returned more than 7,000 pictures and had covered the great majority of the surface. Enough for the first true global map. That map showed a planet divided, with heavily cratered ancient highlands across most of the southern hemisphere and smoother, lower, younger plains across much of the north. And it showed that Mars had a history of volcanism, faulting, wind and water, spread unevenly in time and place. The names carried over from the telescopic era, the seas and bays and lands, were retired as descriptive terms and kept only as labels, and a new nomenclature was drawn up for mountains, canyons, valleys and plains that no one had known were there. The two spacecraft that followed carried something the earlier missions had not: a machine designed to stop. Each Viking was a pair, an orbiter and a lander joined together for the crossing, and each lander was sealed inside a capsule that had been heated in an oven before launch to reduce the chance of carrying terrestrial microbes to a place where the search for life was about to begin. They left Earth in the summer of 1975, some weeks apart, and spent the better part of a year in transit. And the first of them slipped into orbit around Mars in the middle of June 1976. The original plan had been to land on the 4th of July, a date chosen for reasons of national anniversary rather than of geology, but the orbiter's first close pictures of the intended site in Chrysoplanitia showed ground that looked rougher than the planners had hoped, scattered with what appeared to be channels and blocks, and the descent was postponed while the cameras searched nearby for something flatter. Earth-based radar was used in the same weeks, sounding the ground from a distance to estimate its roughness at scales the cameras could not resolve. Only when a patch had been examined from both directions was the landing approved, and Viking 1 separated from its orbiter and entered the atmosphere on the 20th of July, 1976. The descent had 3 stages, each suited to a different part of a very thin atmosphere. First came the aeroshell, a blunt heat shield that took the brunt of entry and shed most of the spacecraft's speed by friction, while instruments inside it sampled the gas streaming past and measured how temperature and density changed with altitude, giving the first direct profile of the Martian air from the top down. Then, a few kilometers above the surface, and still moving faster than sound would move in that thin gas, a parachute opened, slowing the lander further, but not nearly enough, because a parachute in air that thin can only do so much. In the last seconds, 3 rocket engines took over, each with a cluster of small nozzles rather than a single throat, an arrangement chosen so that the exhaust would spread and disturb the ground as little as possible, since the soil beneath the lander was about to be analyzed and no one wanted it contaminated by rocket products. The 3 legs, fitted with crushable aluminium honeycomb inside them, absorbed the last of the impact, and the spacecraft settled upright on the plane. The first image returned was not a landscape, but a study of one footpad and the ground immediately around it, taken within minutes of touchdown, partly to see whether the lander had sunk, and partly because if the spacecraft failed early, that single frame would at least show what the surface was made of. It showed fine-grained material, pebbles, and no sign of sinking. The panorama that followed, built up line by line as a facsimile camera scanned slowly across the scene, showed a plain strewn with rocks of many sizes out to a gently undulating horizon, drifts of fine bright dust banked behind some of the larger blocks, and a sky that was not the dark blue some had expected, but a pale ochre, colored by dust suspended in the air. One large boulder within reach of the cameras was informally called Big Joe, and it was photographed repeatedly over the following months as the light shifted across it. Viking 2 arrived 6 weeks later, on the 3rd of September, and came down in Utopia Planitia at a considerably higher northern latitude, some 4,000 kilometers away, and in terrain of a different character. Its plane was flatter, more evenly covered with angular blocks, with fewer drifts, and the lander came to rest slightly tilted with one leg on a rock. In the winter that followed, its cameras recorded a thin white coating on the ground between the stones, appearing over weeks and vanishing again, which was interpreted as a frost of water. Ice condensing onto dust grains rather than a snowfall of carbon dioxide, since the temperatures recorded were too high for the latter. Both landers carried a meteorology boom that unfolded to hold sensors clear of the body, and from those sensors came the first long weather record from the surface of another planet. At Chryse, the temperature ran through a daily cycle of roughly 50 degrees Celsius, from lows near -85 before dawn to highs in the region of -30 in the early afternoon of summer, never approaching the freezing point of water at any hour. Atmospheric pressure stood at a small fraction of Earth's, close to 7 or 8 thousandths of it, and, more interestingly, it did not hold steady. It fell through the southern autumn and rose again months later, varying by something like a quarter to a third over the Martian year, because a substantial portion of the whole atmosphere was freezing out onto the winter pole as solid carbon dioxide and then returning to the air when the sunlight came back. That seasonal breathing had been predicted from theory, and here it was, written in a barometer trace that ran for years. Winds were generally light, a few meters per second, shifting direction on a daily rhythm, with stronger gusts recorded during the great dust storms that arose in the southern summer and spread until the sky over both landers dimmed. The entry measurements and the landers together settled the composition of the air. Carbon dioxide made up about 95% of it. Nitrogen, which no earlier instrument had detected, made up a few percent, and argon rather less, with small amounts of oxygen and carbon monoxide, and a trace of water vapor that varied with season and site. The relative abundances of the isotopes of nitrogen and of the noble gases carried information about how much atmosphere the planet had lost to space over its history, and those numbers have been used ever since as a constraint on models of Martian climate in the distant past. Each lander had a jointed arm ending in a scoop with a sieve, and with it they gathered soil and delivered it into instruments inside the body. An X-ray fluorescence spectrometer measured the elements present. Silicon and iron dominated, with magnesium, aluminium, calcium and titanium, and, more notably, a proportion of sulfur far above what is usual in terrestrial soils, along with chlorine. The two sites, thousands of kilometers apart and geologically distinct, gave almost the same answer, which suggested that what the scoops were sampling was not local rock ground down in place, but a fine dust distributed across the whole planet by wind. Small magnets mounted on the sampler and on the lander body picked up particles from every scoop, indicating a magnetic mineral, probably an iron oxide, mixed through the dust at the level of a few percent. 3 biology experiments sat inside each lander, all of them designed to look for metabolism rather than for organisms. One moistened a soil sample with a nutrient solution and watched the gases above it. One added a nutrient whose carbon had been made radioactive, so that any carbon dioxide released by something consuming it could be detected by its radioactivity. One kept the soil dry, exposed it to labeled carbon dioxide and light, and then heated it to see whether any carbon had been incorporated into organic material. All 3 registered something. The moistened sample released oxygen quickly and in quantity. The labeled nutrient produced a prompt release of labeled gas that then leveled off, and a second dose given later produced no further release, which is not how a growing population of microbes tends to behave. The third experiment gave a small signal near the limit of its sensitivity. Control samples heated to sterilizing temperatures gave reduced or absent responses in the ways expected. Alongside these sat a gas chromatograph and mass spectrometer, which heated soil to drive off any organic molecules and identify them, and it found none down to the level of a few parts per billion, apart from traces of cleaning solvents left from manufacture. A soil holding living things, or even the remains of past ones, would be expected to hold organic carbon, and there was effectively none to be found. The interpretation most widely accepted then and since is that the Martian soil contains one or more strong chemical oxidants, produced at the surface under ultraviolet light in a dry, unshielded environment, and that these oxidants react with water and with nutrients in ways that mimic metabolism while destroying organic molecules rather than making them. The results were reported as they stood, ambiguous, and the debate over them has continued in the literature for decades, revived by each later measurement of the chemistry of Martian soil. The landers kept working long past their design lifetimes, powered by radioisotope generators that converted the heat of decaying plutonium into electricity. The second lander sent data until the spring of 1980, when its batteries failed. The first continued until late in 1982, when a faulty command ended its communications, having by then recorded more than 2,000 Martian days of weather at one spot on Kryze Planitia. It was afterwards given the name of the scientist who had led its imaging team. For more than a century, the meteorites now known to come from Mars sat in museum drawers without anyone suspecting where they had been made. They were odd, certainly, and catalogued as such. A small handful of stony meteorites made of volcanic rock, containing pyroxene and olivine and glass, with textures that looked like lava that had cooled slowly enough to grow visible crystals. One had fallen in a field in the Haute-Marne region of France in 1815, near a village called Chassigny, which gave the stone and eventually a whole class of meteorites its name. Another fell in 1865 near Shergoti in what is now the Indian state of Bihar, and another in 1911 near the Egyptian village of Nakhla, east of Alexandria, breaking into dozens of fragments as it came down. A fourth fell at Zagami in Nigeria in 1962. These 4 names, 3 of them lending their initials to the informal grouping of Shergottites, Nachlites, and Chassagnites, made up almost the entire known collection for decades, and the question of their origin was not so much unanswered as unasked. What eventually singled them out was their age. Most meteorites are close to 4.5 billion years old, because most of them come from small asteroids that melted early, if they melted at all, and then cooled for good, holding their original minerals ever since. When radiometric dating was applied to the Shergottites, the results came back at a few 100 million years, some of them close to 150 or 200 million, which is very young for a rock delivered from space. A rock that solidified from molten material only that long ago requires a parent body large enough to have retained internal heat over most of the history of the solar system, and no asteroid is remotely large enough for that. The candidates narrowed quickly to bodies with recent volcanism, and Mars, with the enormous shield volcanoes that Mariner 9 had photographed, was the obvious one. The argument was strengthened by oxygen. Oxygen exists as several stable isotopes, and the ratios among them vary slightly from one region of the early solar system to another, so that a given planetary body carries a characteristic signature that ordinary geological processes do not erase. When the oxygen isotopes of the Shergottites, Nachlites, and Chassagnites were measured carefully, they fell together on a line of their own, distinct from the terrestrial line and distinct from the various asteroidal groups, indicating a single parent body shared among them all. That did not name the planet, but it grouped the stones and showed that any explanation had to account for all of them at once. The decisive measurement came from a meteorite found in Antarctica in the ice fields of Elephant Moraine at the end of the 1970s. Antarctica had by then become the most productive hunting ground for meteorites anywhere on Earth. Not because more fall there, but because stones that land on the ice sheet are carried along by the flow and concentrated in patches of bare blue ice where the wind strips the surface away, so that dark objects sit in plain view on a white field with nothing else to confuse them. The Elephant Moraine stone contained pockets of glass formed by the shock of a violent impact, and trapped inside that glass were gases. When those gases were extracted and analyzed in the early 1980s, their composition matched, within the limits of the measurements, what the Viking landers had reported for the atmosphere of Mars. The same proportion of nitrogen to argon, the same distinctive ratio between the isotopes argon-40 and argon-36, the same pattern of xenon and krypton. The glass had been quenched in the presence of Martian air and had kept a sample of it. And since that composition is unlike Earth's atmosphere and unlike the gas in any other class of meteorite, the identification was accepted with unusual speed. The mechanism of delivery is straightforward in outline and demanding in detail. An asteroid or comet strikes Mars hard enough to excavate a crater some kilometers across, and a small fraction of the material near the edges of the excavation is thrown upward faster than the escape velocity of the planet, a little over 5 kilometers per second, low enough that ejection is possible without completely melting or pulverizing every fragment. The pieces then orbit the Sun on their own for a while, and a few of them eventually cross the path of the Earth. How long they spent in transit can be estimated from the effects of cosmic rays, which penetrate a meter or so of rock and produce measurable quantities of rare isotopes at a slow and reasonably well understood rate. Those exposure ages run from a few 100,000 years to about 20 million years, and they cluster, which suggests that the whole collection came from a modest number of separate impacts, perhaps fewer than a dozen, rather than from a steady trickle of unrelated events. There are now on the order of several hundred catalogued Martian meteorites, though the number of distinct arrivals is much smaller because a single fall breaks apart and its fragments are collected and numbered separately, and because the dry deserts of North Africa and Oman, along with the Antarctic ice, yield stones that have lain undisturbed for thousands of years. Only a handful were seen to fall and recovered fresh. Among them, the stones from Chasigny, Shergoti, Nakhla, and Zagami, and one that came down in southern Morocco in 2011 and was picked up within months, uncontaminated by long weathering. What the laboratories have done with this material is difficult to overstate in terms of detail, and easy to state plainly in terms of substance. A rover on Mars carries a few instruments chosen years in advance, weighing a few kilograms, operating in cold and dust with limited power. A terrestrial laboratory can take a gram of rock and apply an electron microprobe, an ion probe, a mass spectrometer of whatever kind is appropriate, thin sections under polarized light, and stepwise heating experiments, repeating any of them as new questions arise, and returning to the same sample 20 years later with better instruments. The Martian meteorites have therefore supplied the most precise mineralogy, chemistry, and chronology available for the planet. From them came the picture of a Martian mantle that is richer in iron than Earth's, and depleted in certain elements in a distinctive way, along with evidence that the planet separated into core, mantle, and crust very early, within a few tens of millions of years of its formation, deduced from the decay products of short-lived isotopes. From the Nakhlites, which crystallized about 1 1/3 billion years ago, came confirmation that volcanism continued long after the planet's youth, in agreement with the sparsely cratered lava plains mapped from orbit. Within the Nakhlites, there are also thin veins of alteration minerals, iron-bearing clays and carbonates and salts, deposited by liquid water that percolated through the rock hundreds of millions of years after it formed and then departed, leaving a record of brief and limited wetting rather than of prolonged immersion. One Antarctic stone found in the Allan Hills in 1984 proved to be far older than the rest. An igneous rock close to 4 billion years in age, and thus a fragment of the ancient Martian crust rather than of any young lava flow. It contains small globules of carbonate, and in 1996 a team of investigators reported in the scientific literature that features within those globules, including grains of magnetite, organic compounds, and shapes at the scale of a few tens of nanometers, might be traces left by microbial life. The claim was examined intensively for years afterwards, and for each feature an explanation was found that required no biology, involving mineral growth from warm fluids, terrestrial contamination, and the ordinary consequences of shock and heating. No consensus supports a biological reading now, but the work drove a lasting improvement in the methods used to look for such traces in very old rocks. A later find from the Sahara, a breccia of cemented fragments containing crystals dated to roughly 4.5 billion years, matched the average composition of the Martian crust as measured from orbit more closely than any previous meteorite, and held more water in its minerals than the igneous samples did. It is a reminder that the collection is not a random sample of the planet. Impacts launch strong, coherent rock, mostly volcanic, mostly young, from places nobody chose, and the sedimentary layers and clay beds that rovers have found in such abundance are scarcely represented at all. The questions asked of Mars changed shape in the 1990s. Whether water had ever existed there was no longer seriously in doubt, since the dry channels photographed from orbit 2 decades earlier demanded some fluid, and the thin, cold air of the present demanded that the fluid be gone. What remained was harder and more patient work. To find where the water had gone, how much of it was still present as ice, in what form the remainder had been locked into minerals, and over what stretches of time the planet had passed from one condition to another. That work has been done by a long relay of orbiters carrying cameras, spectrometers, neutron detectors, and radar sounders, and by landers and rovers scratching at the surface in a handful of chosen places. And the picture it has assembled is neither the warm, wet Mars of 19th century hope, nor the plain, dead, cratered ball that the first flybys seemed to show. The first of the modern orbiters settled into its mapping path around Mars in the late 1990s and carried a laser altimeter that fired pulses at the ground and timed their return, building a topographic model of the whole planet with a vertical precision far beyond anything drawn from photographs. That model showed the northern lowlands to be remarkably flat and smooth, smoother over great distances than the ocean basins of Earth, and it measured the polar deposits as broad, low domes of layered material some kilometers thick, cut by spiral troughs and terminating in scarps where the layers stand exposed. The same spacecraft's camera found small gullies incised into the walls of craters and troughs, fresh-looking, unfilled by dust, and the debate over whether they were carved by seeping water or by the seasonal coming and going of carbon dioxide, frost has continued since, with the weight of later evidence resting on the frost. A following orbiter, arriving at the beginning of the new century, carried instruments that counted neutrons and gamma rays produced when cosmic rays strike the soil. Hydrogen is unusually effective at slowing neutrons, so a hydrogen-rich layer near the surface announces itself by suppressing the flux of fast neutrons escaping to space, and the maps drawn from those counts showed the high latitudes of both hemispheres to be rich in hydrogen within the uppermost meter or so of ground, in quantities most simply explained as ice mixed with soil or as nearly pure ice under a thin, dry blanket. The prediction that followed was specific and testable. Dig at a high northern latitude and you will strike ice at shallow depth. A small lander set down on the northern plains in 2008 scraped a trench with its arm and exposed bright material that vanished over the following days by sublimation, which is the behavior of ice and not of salt. Its instruments also found perchlorate salts in the soil, compounds that lower the freezing point of water considerably and that complicate any simple accounting of what liquid might be possible in the present climate. Radar has proved the most direct instrument for looking beneath the surface. 2 sounders, one on a European orbiter and one on an American one, transmit long wavelength pulses that penetrate rock and ice and read the echoes from buried interfaces. Both found the polar layered deposits to be nearly clean water ice throughout their thickness. with the internal layers traceable across hundreds of kilometers. And the volume held in the northern deposit alone is enough, if it were melted and spread evenly across the planet, to make a global layer some tens of meters deep. The same technique found ice far from the poles, in the mid-latitudes, buried beneath a meter or two of dust and rubble, forming sheets and lobate aprons around the bases of massifs that had long been suspected of being ice-cored on the strength of their shapes alone. Where a fresh impact punches through the covering, cameras have caught the exposed ice as a bright patch that dulls and shrinks over the following seasons, and dozens of such windows have now been catalogued. Mineralogy has told the older part of the story. Spectrometers on 2 orbiters, one European and one American, mapped the absorption features of hydrated minerals across the planet and found a distinct pattern in their distribution. Clay minerals, the phyllosilicates, which form when rock is altered by water at moderate temperature and near neutral acidity, occur chiefly in the oldest and most heavily cratered terrains of the southern highlands, in the walls of craters and canyons where deep material is exposed. Sulfate salts, which form from more acidic and more evaporative waters, occur in younger deposits, in layered mounds within basins and in the thick sequences around the equatorial canyons. Younger still are the broad expanses where the only alteration product is the fine ferric dust that gives the planet its color, produced slowly and without much liquid at all. The straightforward reading of that sequence is that Mars had an early period in which water acted on rock widely and for a long time, a middle period in which water was scarcer, saltier and more acidic, and a long final period, continuing now, in which the surface has been oxidizing dryly under a thin atmosphere. The rovers have tested that sequence at ground level. One of the 2 small vehicles landed in 2004 came down on a plain of sulfate-rich sandstone and found within it the mineral jarosite, which requires acidic water to form, along with small hard spheres of iron oxide weathered out of the rock, and cross-bedded structures of the kind left by shallow flowing water and by wind-driven ripples. The other rover, on the far side of the planet, worked its way into older hills and found deposits of nearly pure silica of the sort produced by hot water or steam passing through rock, and outcrops rich in carbonate. A larger rover set down in 2012 inside a crater with a layered mountain at its center, and within its first months, it drove over beds of cemented gravel whose pebbles were rounded, which is what running water does to stone and what wind does not. Drilling into fine mudstone nearby, it found smectite clays, magnetite and sulfur compounds in proportions indicating a lake of near-neutral water that persisted long enough to lay down mud. And as it has climbed the layers of the mountain, it has passed from clay-bearing rock into sulfate-bearing rock. Walking upward through the same transition the orbital maps had sketched from above. A still later rover landed in a crater holding what appears to be a river delta, built where a channel entered a standing body of water, and it has been drilling and sealing samples of those deposits and of the carbonate-bearing rocks nearby for possible return to Earth. Behind all of this sits a slower clock. Mars has no large moon to steady it, and the tilt of its axis therefore wanders far more than the tilt of Earth, oscillating over tens of thousands of years and swinging, on longer timescales, between values low enough to leave the poles in near-permanent cold and values high enough that the polar regions receive more summer sunlight than the equator. Its orbital eccentricity varies as well, and the season during which it passes closest to the Sun drifts steadily around the year. At high tilt, the polar ice becomes unstable and water migrates towards the middle latitudes, where it accumulates as the buried sheets and mantles now detected there. At low tilt, the movement reverses and the caps rebuild. The layers within the polar deposits are read as the record of those cycles, alternating brightness and dust content laid down season upon season, and the mid-latitude glaciers, which lie under insulating debris in places where ice could not form today, are understood as leftovers from a recent high-tilt interval rather than as relics of the ancient past. What has been lost from the system is measurable in the atmosphere itself. Hydrogen exists in two forms, ordinary and heavy, and the lighter escapes to space more readily. So a planet that has lost water leaves the remainder enriched in the heavier kind. Measurements of Martian water vapor and of water bound in ancient clays show such an enrichment by several times the terrestrial value, and an orbiter dedicated to the upper atmosphere has watched the escape happening, atom by atom, driven by ultraviolet light and by the solar wind on a world without a global magnetic field to deflect it. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well, and see you very soon.